Hey guys, welcome back to OGLDEV. Today we're adding mouse support and we will implement the rotations that are caused by the movement of the mouse using Quaternions. But first, an apology. I made a serious mistake a couple of tutorials back in tutorial 13, where in the last slide I developed the final camera transformation matrix by simply combining the translation and the UVN matrices together, as we can see right here. This, of course, is incorrect. And if you actually perform the matrix multiplication, you will see that you are getting a different result altogether. Okay, so therefore, the correct course of action is to generate the two matrices separately and simply multiply them together to get the final matrix. We can see the fixed code right here in the implementation of the function initCameraTransform of the matrix 4f class, which is located in common/math_3d.cpp. We create the two matrices. The first one is a standard translation matrix, which takes the negative of the camera position, as usual. The second matrix has the UVN vectors as rows in the top left 3x3 submatrix. We multiply them together and copy the result into the current matrix to make it a full camera transformation matrix. Now let's go back to our business with the mouse. There are many different behavior types of the camera that can be implemented when using a combination of a keyboard and a mouse. So let me show you the way I planned to make this work here. And for that, I'm going to jump ahead and use a future tutorial with support for model loading. This is the famous Sponza Palace from Dubrovnik, Croatia. It is from the 16th century and it became especially famous when Crytek used it in 2010 to demonstrate global illumination. It helps us demonstrate an environment which is 360 degrees around the viewer. Our usage model is very simple. We want to look up when the mouse goes up and down when it goes down, left and right also as expected. Moving the mouse always changes the target vector of the camera, but not its position. The keyboard controls the position of the camera, but not its target vector. If you press left or right, you are strafing, like in a first-person shooter. If you press up, the camera moves forward along the target vector, and vice versa if you press down. In order to do a full circle, you only need to move the mouse cursor to the leftmost or rightmost column of pixels. As you can see right here, my hands are off the mouse, but the camera keeps turning until I move the cursor away from the edge of the screen. In terms of look up or down, we can only turn the camera along an arc of 180 degrees. We cannot do a full vertical circle as if it is a flight simulator, and this helps us keep the camera relatively simple. In this model, we basically have two axes of rotations, and each axis has its own rotation angle. The first angle is very simple. It changes when the mouse travels left or right, and this causes the camera to spin around the y-axis of the world. So even when the camera looks up, which causes its v-axis to tilt backwards, it keeps rotating around the y-axis of the world. Let's look up and then do a full circle, and you can see that our target vector keeps pointing up. We call this angle of rotation the horizontal angle. The second axis of rotation is a bit more complex. The angle around this axis is called the vertical angle, and it changes when the mouse goes up or down. As the camera spins around the v-axis, the u vector that goes to the right is also spinning because it must maintain its 90 degrees from the n vector, which is the direction that the camera is looking at. When the camera looks up or down, it basically rotates around the u vector, so we must make sure to rotate around the current u. We can update the target vector to follow the horizontal and vertical angles in different ways, but the method that I'm going to present today is based on Quaternions. Now, Quaternions are a mathematical concept, and they were invented in 1843 by this Irish gentleman, Sir William Rowan Hamilton, who was a professor of astronomy in Trinity College, Dublin. Quaternions are somewhat complicated, and a professional mathematician can probably talk about them for hours, but here I'll try to explain just what we need in order to calculate our camera rotations. If you're interested, you can find tons of videos on this subject on YouTube. I'll put a link below to a couple of resources that helped me a lot in researching for this episode. I'll be following the approach suggested by this book, the 3D Math Primer, which describes the quaternion from a geometric perspective rather than using complex numbers. The quaternion is composed of a scalar component denoted W and a vector denoted V. The following short and longhand versions are equivalent. The quaternion represents a rotation around a vector. You might be thinking that V is this vector and W is the rotation angle, but actually they are not. If we have an axis of rotation n and an angle of rotation theta, then the W in the quaternion that corresponds to this rotation equals to the cosine of half of theta, and the V vector is calculated by multiplying n by the sine of half of theta. This is how the quaternion looks like in this case, in the short and longhand versions. So V is basically the n vector scaled by a factor of sine of half of theta, but they both point in the same direction, they just have different length. The reason that we use only half of theta rather than the entire theta is that when we get to the actual part of using the quaternion for rotation, you will see that we are applying two quaternions on the rotated point, one on each side. More on this shortly. As you can see, the quaternion is kind of a four-dimensional vector, and we calculate the magnitude or the length of the quaternion in a similar fashion to any other vector by summing up the power of 2 of the w, x, y, and z components, and then applying a square root on the result. Same as in vector magnitude, when the length of a quaternion is 1, we call it a unit quaternion. From now on, that's the only type of quaternions that we are going to use. Okay, so unit quaternions. Now let's define the quaternion conjugate as the quaternion that cancels the rotation of another quaternion. We denote this quaternion as Q star, and it is very easy to construct. We simply flip the direction of the V vector by negating it. So now, the same angle of rotation on the flipped vector will take us back to the original location. The quaternion conjugate leads us directly to the rather mysterious equation of using the quaternion for rotation. So if we have a point P and the rotation quaternion Q, which we know is a unit quaternion, then in order to rotate P around the vector V by theta degrees, we need to multiply Q with P, and then multiply the result by the conjugate of Q. Here we can see the two halves of the rotation that I mentioned earlier. In order to multiply the quaternion by a point, we can extend the point into a quaternion by having 0 in the W component of the quaternion and using the point as its vector part. Explaining why this formula is correct requires going deeply into complex numbers, and it is a bit out of scope for this video. I may explore this more in a future video. Again, the reason that this formula works with the conjugate is because the rotation quaternion is a unit quaternion. Otherwise, we have to use the quaternion inverse, which is a bit more complicated because it requires dividing the conjugate by its length. But as I said, the conjugate works here just as well. The only thing we have left is to define the operation of quaternion multiplication. So if we have two quaternions, Q1 and Q2, then when we multiply them together, we get another quaternion whose W part is the product of the W components of Q1 and Q2 minus the dot product of the two corresponding vectors. The vector component is much more complex. We need to multiply the first W by the second vector, add the second W multiplied by the first vector, and finally add a cross product of the two vectors. Phew. If we write this as a longhand version, we get the following equation.
Yeah, piece of cake.
Let's do a rundown of the major points of the new code before we dive in. We mainly need to do the following three things. We need to register a callback function to trap the movements of the mouse. In the callback function, we need to convert mouse movements into angles of rotations and update the camera vectors accordingly. And for that, we will use our new knowledge of quaternions. In the main render function, we need to handle the case where the mouse rests on one of the four edges of the screen, and in this case, update the target vector of the camera. Now in this tutorial, I decided to switch to full screen mode, which seems appropriate for our camera with the mouse because it kinda works like a first-person shooter camera. To do that with FreeGLAT, we need to call GLAT enter game mode, but before we do that, we need to initialize a game mode using this somewhat bizarre game mode string. The format of this string is the width of the window, followed by the letter X, then the height of the window, then the @ symbol, and finally a bit per pixel, which is basically the color depth. We prepare this string right here by calling snprintf with a buffer in the first parameter, its length in the second parameter, and then a regular printf string with the window width and height as parameters. Note that not all resolutions work. For example, the native resolution of this monitor is 2560 by 1440, and this works. Yet the full HD of 1920 by 1080 doesn't work for some reason. I don't know. Next, I refactored the initialization of the GLAT callback functions to this function, init-GLAT callbacks, which is up here. You are familiar with the first three callbacks, and we've added the two keyboard callbacks in the last episode. Here, we're registering a passive callback function for the mouse using GLAT passive motion func. Passive motion means that the mouse moves without any of its keys pressed. If you want to trap mouse movements while a key is pressed, you use GLAT motion func. The mouse callback function is defined right here. It receives the location of the mouse as X and Y coordinates and passes them along to our game camera by calling the camera class function onMouse. In order to handle the case where the mouse rests without movement on one of the edges of the screen, we also have a camera callback function onRender, which is called in the main render function right here. These are the key changes in the main application code. Most of the remaining changes are in our camera class, which we will now review. Note that we now have a new revision of the camera in camera H and camera CPP in this directory, OGLDEV/tutorial15_YouTube. You can review the changes by comparing these files to the previous version in tutorial14_YouTube. Let's go over to the camera class declaration in camera.h. You can see that we have a new constructor that, in addition to the window width and height, also takes the position of the camera, its target vector, and its up vector. You can also see here the declarations of the two new functions onMouse and onRender. We have a few new private attributes. First, the horizontal and vertical angles that we talked about in the background section. We also have 4 Boolean values that indicate whether the mouse is resting on one of the edges of the screen. Finally, we have a 2D integer vector to store the current location of the mouse. Let's review the new constructor in camera.cpp. In addition to storing the window width and height, we also store the position, target, and up vectors. We must normalize the target and up vectors just in case the caller didn't deliver unit vectors. Next, we call init, which is a new private function, which is also called by the other constructor. The main job of this function is to initialize the horizontal and vertical angles based on the initial values of the target and up vectors. This, of course, needs to be done only once, and from now on, we do this in the onMouse function. As we did in the tutorial about rotations, we can use the Z value to calculate the horizontal angle of the target vector. The problem is that we want a full 360 angle, whereas the arcsine of z, as it goes from -1 to 1, will only give us the range of minus 90 degrees to plus 90 degrees. What I did is to use the arcsine function on the absolute value of z, and then check the sign of x and z to determine the quadrant of the circle where the target vector is located. To do that, we initialize the vector on the xz plane by taking the x and z components from the target vector and the 0 in the y component. After normalizing this vector, we translate z into degrees by calling a sin on the absolute value of z. As z goes from 0 to 1, the angle goes from 0 to 90. Remember that a sin returns a value in radians, so we need to convert this back to degrees. Next, we check the sign of x and z and calculate the final horizontal angle by finding out the quadrant of the target vector. When the angle is 0, the sine function of 0 returns 0, so z is 0 and the target vector points to the right. As the angle grows, the target vector rotates clockwise, so when z is negative and x is positive, we are on the bottom right-hand quadrant, and we can simply use the angle as is between the range of 0 and 90 degrees. Next comes the bottom left-hand quadrant, so we calculate the final angle by subtracting our angle from 180. We do the same with the top left-hand and right-hand quadrant for the range of 180 to 270 and 270 to 360 degrees, respectively. The calculation of the vertical angle is simpler because it only goes between 90 degrees when the camera is looking down and minus 90 degrees when it is looking up. This time we use the asin function on the y component of the target vector, but we need to take it in the negative because the asin of positive 1 is 90, which matches the angle where the camera is looking down. At the end of this function, we reset all the on-edge boolean flags to false and set the initial mouse position to the center of the screen, which I saw is the default behavior when switching to full screen mode. If you're not in full screen mode, it may require some different logic. Now let's see what happens when FreeGLAT informs us that the mouse has moved. We handle this case in the onMouse function. We start by calculating a delta x and y by subtracting the old mouse location from the new location. We can now store the new location in the class attributes and update the horizontal and vertical angles based on the deltas. When the mouse goes to the right, the delta x is positive, so this increases our horizontal angle, which goes clockwise. When the mouse goes down, it increases the vertical angle because in OpenGL, y is 0 at the top of the screen and the maximum value is at the bottom of the screen. When the delta x or delta y is 0, we check whether the mouse is resting on the corresponding edge of the screen and initialize the on-edge boolean flags accordingly. As you can see, we're not checking for the exact first or last row or column pixel. Instead, there is a margin of 10 pixels by default that makes the camera more user-friendly when you're not in full screen mode, and it is more difficult to hit the precise location at the edge of the window. At the end of this function, we call update, which takes care of updating the target and up vectors based on the new horizontal and vertical angles. We start by initializing the y-axis of the world, which points directly up. We set the initial view vector to point to the right and rotate it around the y-axis by the horizontal angle. This will be done with Quaternions, but let's complete this function first. With the view vector rotated by the horizontal angle, we perform a cross product of the y vector and the view vector. As we already saw in the previous episode, this gives us the u vector of the UVN system. After normalizing this vector, we rotate the view vector around it by the vertical angle this time, again using Quaternions. We can now set the target vector of the camera to the result and recalculate the up vector as usual. Now let's see the implementation of the vector rotation using Quaternions. The vector3f class has a rotate function in command /math_3d.cpp. This function takes in an angle and a rotation axis v. We can now see the implementation of the quaternion rotation formula. We start by initializing a quaternion for the angle and the rotation axis. We calculate the quaternion conjugate and then multiply the rotation quaternion on the left-hand side on the current vector instance and the conjugate on the right-hand side. Finally, we initialize the current vector based on the result of this multiplication. Now let's dive into the quaternion itself, okay? The quaternion is a very simple structure with x, y, z, and w components. It is initialized exactly as we saw in the background section by calculating the sine and cosine of half of the rotation angle and setting the vector part to be that sine result multiplied by the vector and the w to be the cosine result. The conjugate is also very simple, just need to negate the vector part. Finally, we have two implementations of the multiply operator. The first one is for multiplying a quaternion by a vector, which is the left-hand part of the rotation formula, and the second one is for multiplying two quaternions, which is the right-hand part of the formula. They are almost the same, and the only difference is that in the quaternion vector version, we don't need the left column because the w in the vector is 0. I won't go too deeply into this. This is simply a direct implementation of the formula that we saw in the background section. The last major function that we need to review in this class is onRender, which is called from the main render function. This function simply checks whether the mouse is resting on one of the edges of the screen and increments or decrements the corresponding angle by some pre-configured value. In the case of the vertical angle, we also make sure to limit the range of motion between plus and minus 90 degrees. If indeed one or both angles were updated, we call the same update function as before to translate the angles into the camera vectors. Before we wrap up, let's go back to the main application code, and we can still see the camera instance in the global section, but this time we are using the extended constructor so we can plug in different target vectors. For example, let's point the camera a bit upwards by setting the y component of the target vector to 1/2. This seems to work okay. Now let's turn the camera slightly to the right by setting the x to also to 1/2. And as you can see, this also works okay. I hope I didn't confuse you too much with this whole quaternion business. I feel that I've barely scratched the surface with this important topic, but I wanted to strike a good balance between understanding quaternions enough so they can become practical and not sacrifice the progress that I want to make with the main topic of this series, which is, after all, OpenGL. As I said, I may do a follow-up session on quaternions sometime in the future. Now, this implementation of the camera that you saw is really the best in the world. No, I'm kidding, of course. There's definitely lots of things that can be improved, and I'm sure different people are implementing the same general concept in different and much better ways. So let me know how you implemented your camera. I'd love to hear your thoughts on this, okay? Please hit that like button if you enjoyed this episode and subscribe to my channel. Check out my website at OGLDEV.org for more tutorials. Thanks for watching, and I will see you soon.